Good morning, grade 10s, and welcome to the final main lesson in the grade 10 science chemistry unit. And in this lesson, we're going to be covering two last final topics in chapter 7. And that is section 7.5, neutralization reactions, and section 7.8, which is acid precipitation and basically acids and bases in real life. So, just to recap what we learned back at the beginning of this week, at the beginning of chapter 7, we learned that acids and bases are an important category of substances that we need to know about. We learned that both acids and bases have important properties. For example, acids and bases are substances that interact with water, so water needs to be present. In order for you to have an acid or a base, you need to have a substance mixed with water. We also learned that these substances mixed with water are good conductors of electricity, but they do differ in that acids tend to donate hydrogen ions, or we also call them just protons. Acids tend to donate protons to water, while bases do the opposite. They tend to steal or accept protons from water. And that results in different properties. Acids react well with metals and with carbonates and other bases, while bases don't really react with metals and they don't react with carbonates, because carbonates are bases. Bases tend to react with acids. They both can be dangerous, though. They both can be strong and weak. They both can be corrosive. And they both have different. We have a way of measuring them in two different directions. We have what's called the pH scale. The pH scale measures acids and bases on a number line between 0 and 14. 7 is neutral. Pure water would be defined as your 7 neutral substance. Acids have a pH lower than 7 and bases higher than 7. So that brings us to the next topic here. What happens when you mix an acid and a base together? Once again, we're following the same handout that you downloaded for the last section, lesson 7. This is lesson 8, and it's the same handout. So you did the first 3 pages of that handout earlier this week, and now for today and tomorrow, the last 3 pages of that same handout. So have that handout out in front of you and ready to fill in as we go through this. Also, I should note this is going to be a longer video again, but it's a 2-day lesson once again. So you have today and tomorrow to work on this lesson if needed. So let's get started. A neutralization reaction is what we would call it when we neutralize acids and bases. So think about what that means. You have acids on one end of the pH scale, and you have bases on the other end of the pH scale, and they're both, the farther away they are from 7, the stronger and the more dangerous they are. So to neutralize them is that we want to try and bring them closer to 7. We want to try and neutralize them, bring them closer to neutral. Remember, 7 is neutral. So what do? Well, if we have an acid and we want to neutralize it, we add a base. Or if we have a base and we want to neutralize it, we add an acid. So that's the cool thing about acids and bases, is they cancel each other out. And they even out the pH. They bring the pH closer to 7. So let's look at an example here. Hydrochloric acid, that's HCl. When I add sodium hydroxide to that, I get water and sodium chloride. Let's have a look at this reaction for a minute. So I'm going to talk you through this video here. So we have 2 equal concentrations of sodium hydroxide or hydrochloric acid on the left, sodium hydroxide on the right. The man in the video is adding an indicator, just like the red cabbage was an indicator. This particular indicator is just called universal indicator. Notice when he has it in the dropper, it's green, it's neutral. But when he adds the green substance to hydrochloric acid, it's a pink color. But when he adds it to sodium hydroxide on the right, it's a dark blue or purple color. And that's what universal indicator does. Strong acids are pink, strong bases are blue. But notice now when he mixes the two together, the indicator goes back to green, back to neutral. So mixing the two mixing the hydrochloric acid and the sodium hydroxide causes a neutralization reaction. Okay, so what happened there? Well, look at the reaction. We have hydrochloric acid, so we have HCl. So there's the H. The H is what makes it an acid, right? It donates its hydrogens to water. Sodium hydroxide, notice anything with hydroxide in the name, that's going to make it a base. And when we mix these two together, what's going to happen is the hydrogen's going to come in. It's going to kick the sodium out. The sodium's going to go over and join the chlorine. The hydrogen's going to stay with the hydroxide. And what you get is water. Remember, HOH or H2O. It's just two different ways of writing the same thing, water. And then sodium chloride, which is a salt. What type of reaction is this? You've seen this type of reaction before. Think about the four basic types that we've seen. Remember, synthesis, decomposition, single displacement, double displacement. Which type of reaction is this one? Well, if you said double displacement, you're right. This is a double displacement reaction. And all acid-base neutralizations, sorry I cut that word off there, but all acid-base neutralizations are the same. They're all double displacement reactions in which you mix an acid and a base together to get salt and water. All right, let's get to the worksheet. So in the worksheet, the first question that you see is what would be an effective way to clean up a large acid or base spill? What you would do is, well, you think about it. If I have an acid-base spill, what would you do? The textbook, at the beginning of section 7.5, the textbook has a description of an accident that occurred in Niagara Falls in 2007. A truck that was carrying a strong base, potassium, I think it was potassium hydroxide, ran off the road and ran into a hydro pole, and just the angle at which it collided, it caused a rupture of the tank that was carrying aqueous sodium hydroxide. Sodium hydroxide dissolved in water, so a strong base. And it started spilling all over the roadway. This is in the city, so it's a very touristy place, right? So there's a lot of people around, a lot of people live there or traveling, and there was a danger because that's a strong base, it's corrosive. People were in danger. So the fire department was called, and when the firefighters arrived and they found out what was spilling onto the roadway and into the ditches, think about what was a very quick thing that they could do to try and clean up this strong base. Well, based on what we just saw, we want to neutralize that base. We want to add something to it that can bring the pH from 13 or 14 down closer to 7. And so they want to add an acid. Now, they don't want to add necessarily a strong acid because that also is harmful and is dangerous for people walking down the sidewalk. But if they add a whole bunch of maybe weak base, that might be an effective way. Weak acid. If they add a whole bunch of weak acid to the base, weak acid is not necessarily as harmful, and the weak acid can neutralize the base and bring it closer to a pH of 7. And that's exactly what the firefighters did. They went to the nearest grocery store. They bought 40 large bottles of cola, so Coke or Pepsi or whatever. Because cola is an acid, but it's not harmful, right? It's a weak acid. We drink it, so it can't be that harmful. It's not great for you. But cola has two acids in it. It has carbonic acid and phosphoric acid. And that weak acid, they basically started pouring those. They stopped the leak in the truck, but then they started pouring those bottles of cola all over the base that was spilling. They neutralized the base. And then they were able to add some absorbent sand-like materials, kind of like a litter box, to clean that up. Okay, so what would be an effective way to clean up an acid or a base? You would neutralize it with the opposite substance. Okay, think of a train derailment. This is stuff that we hear on the news sometimes, and next week you're going to have an activity involving this sort of real life scenario. So think of a train derailing carrying strong sulfuric acid. What would you want to do if that train derailed and started spilling that sulfuric acid into the ground, into the waterway, whatever's nearby? you would want to quickly stop the leak, but also you would want to neutralize that acid with a base, preferably a weaker base that's not going to cause its own harm before it does the neutralization. So something like baking soda would be a weak base that could be added to neutralize the acid. All right, so the definition on your worksheet of a neutralization reaction is this is a type of chemical double displacement reaction in which an acid and a base react together to form an ionic compound. That's a fancy word for a salt and water. A double displacement reaction in which an acid and a base are added together and react to form an ionic compound, a salt and water. The resulting pH is brought closer to 7. Think about what acids and bases have, right? Remember, what distinguishes an acid from a base when it's in water? Well, acids add hydrogen ions to the solution. So when we have an acid, we have lots of H plus ions. Lots of H plus ions. When we have a base, bases are pulling hydrogen away from water. Remember, a base steals hydrogen away from water, so the base is going to steal the hydrogen, and what's left is OH minus. So a base is going to have lots of OH minus, some hydroxide ions. So if we mix acids and bases together, you're basically mixing H plus ions with OH minus ions. Well, think about that simple reaction, right? If I add hydrogen ions, these are also just called protons, and I add protons to hydroxide ions. Oops, sorry, getting messy here. Hydroxide ions. What are we really doing? Well, if you add these two together, you're basically forming a molecule of water. You have the O and the H in the hydroxide, and they have an extra electron. That's why the negative charge, an extra electron. Then you're adding another hydrogen, which is missing an electron. That's why the positive charge. And the charges balance out. The H and the O and the H make a water molecule. Okay? So that's why we always get water formed in a neutralization reaction. Every acid-base reaction is going to look the same. You're going to have an acid. You're going to add a base. You're going to get water. So the H and the OH are going to form water, right? The H and the OH are going to form water. And then whatever's left, a metal and a nonmetal usually, is going to form a salt because it's an ionic compound, a metal plus a nonmetal. Now make sure that you're very aware of the crisscross rules and the charges when you're writing these reactions out. This one works out nicely because you have one hydrochloric acid plus one sodium hydroxide forms one water and one sodium chloride. That's really nice. It's already balanced. You don't need any coefficients, but be careful. There are other examples, and we'll go through a couple where you will need that. So the key takeaway from this lesson is that a neutralization reaction, that is an acid mixing with a base, is a type of double displacement reaction, but you always get water as one of the two products. So here's another example. Again, notice how this is similar and how this is different from the first example. So we have H3PO4. Does anybody know what this is called? This is called, well, it's an acid made from phosphate, so it's called phosphoric acid. Phosphoric acid. This is actually found in POP, phosphoric acid. Does anybody know what this base is called? KOH. This is the base that was mentioned in the Niagara Falls accident example. This is potassium hydroxide. And when we mix these two together, think about what's happening. We have the hydrogens are going to combine with the OHs to form water. In this case, there's 3 hydrogens combining with 3 hydroxides, and therefore we're going to get 3 waters. And then the leftovers are metal, right? A metal, so potassium is a metal. It's going to join with phosphate, which is a polyatomic ion. And we get the positively charged metal, 3 of them, combining with 1 phosphate. Why? Because phosphate has a 3 minus charge, and potassium has a 1 plus charge. 1 plus charge. So it makes sense that it would be K3PO4 because of the crisscross rule. But we would still call that a salt, potassium phosphate. It's an ionic compound, it's a salt. Same pattern, this one required some 3s to be balanced out. Okay, sometimes they are not always as clean cut as this. So here's a tricksy example. Here we see one where you don't get the water is not there obviously. I would never ask one of these on a test though. I would always just ask like the normal acid plus base, salt plus water example. But just to show you, it's not always, there's always kind of weird exceptions. So here we have hydrochloric acid. Notice there is water here because it's aqueous, right? And this is ammonia. Ammonia also has water present because it's aqueous. So these are dissolved in water and they're mixing together to form ammonium chloride. And there's still water because it's aqueous, but we don't actually need to show it in the reaction because those waters were already there. So the water is implied but not explicit. Here's another tricky example. I'm going to have to move myself over to the left here for this example, I think. So here we have sulfuric acid mixing with baking soda, sodium hydrogen carbonate. Remember, anytime you see carbonate, you know it's a base. Sulfuric acid's got the H at the beginning. There's the acid. And we get the sodium combining with the sulfate. And then the hydrogen combining with the carbonate to form a weak acid hydrogen carbonate. But that's immediately going to form water and carbon dioxide. So this is a little bit of a weird example in that the water is delayed a little bit, and you're going to get a whole bunch of fizzing bubbles. Anytime you're familiar with this, if you ever add vinegar to baking soda, whenever you have baking soda and adding an acid, you're going to get carbon dioxide bubbles. So you get that fizzy reaction. These are unusual examples. This is not the norm. On the test, I would stick with the normal examples. Okay? So that's it for the first section, section 7.5. You could pause the video now and work on some practice. Page 281, number 2, 4, 6, 8, 9, 10. Or if you want to save your practice till the end of the video and just keep watching, you can do that as well. So I'm going to keep going into section 7.8. Section 7.8 tries to make this even a little more real for us. Why is this important for us in real life to understand acid-base reactions and in our everyday life? How is this relevant for us? Like, what if I'm never going to go into chemistry or even go into any scientific field? Who cares? Why do I need to know this? So we look at a case study in section 7.8 of acid rain. Acid rain, or acid precipitation, is what happens when you get acids into the air and mixing with the water in the clouds. And then the rain that falls on you, or it could be snow or sleet or hail or fog, is acidic. How is that harmful, and is there a way that we can avoid that? So I would pause the video if you're able to. Go to this YouTube link here, and I put the link in the ESB lesson plan as well, and watch a short, it's only 2-minute long video from National Geographic, just introducing you to what is acid rain. But if you look at the picture here as well, so this is a statue, and look at what's happening to this statue. This statue is made out of limestone, which is a type of basic substance, calcium carbonate. And over time, acid rain falling on this statue is eating away at the statue, and you can see it's become disfigured. And this is not just statues, but lots of buildings are produced from limestone, and it also can be very harmful to the environment. So let's get into that. But watch this National Geographic introduction before moving on to the next slide. So continuing our worksheet, what is acid precipitation? Well, here's the definition. Any precipitation, remember precipitation is a fancy word that we mean for any time moisture is coming down from the atmosphere down to the earth. So typically rain, snow or freezing rain, sleet, hail, dew, etc. Any precipitation in which the pH of that liquid is less than the normal pH of rain. And the normal pH of rain is 5.6. Now you might be asking yourself, why is that? Why is the pH of rain normally 5.6? Shouldn't rainwater be mostly pure water? Shouldn't it be like 7? I mean, the pH of pure water is 7. So why is the pH of rain 5.6? Why is it slightly acidic? The reason for that is because there's lots of carbon dioxide in the atmosphere. And we continue to put carbon dioxide into the atmosphere, right? Animals and humans, we breathe out carbon dioxide. We also spew out carbon dioxide in many different forms. So there's lots of carbon dioxide in the atmosphere. It's actually a greenhouse gas. It's one of the things that's contributing to climate change and global warming. Carbon dioxide, you might remember this from the lesson earlier this week, lesson 7, that when you mix carbon dioxide with water in the air, you get a weak acid, carbonic acid, H2CO3, aqueous. H2O is a liquid, CO2 is a gas. And so that weak acid is what makes normal rain 5.6. And that's okay. That's not that acidic. It's not going to be that harmful. When we call something acid rain, we mean it has an even lower pH. It's even more acidic than normal. This does not always have to be liquid or solid rain. It can also sometimes be pollutants in the air that fall to the ground and then mix with water on the earth. And that's called dry deposition. Dry deposition is the process in which acid-forming pollutants fall directly to the earth in a dry state. And when they combine with water, let's say in a puddle, in a lake, in a stream, in a river, then they form an acid there. So this is also a form of pollution. How do we get acid rain? Well, the main two contributors to acid rain are these two chemicals right here. You can see them up here. Sulfur dioxide, which is primarily produced in factories and industrial processes. So almost every town and city in Canada and around the world has factories of some sort, right, that are producing something. And there's always byproducts in these industrial processes. And they often produce exhaust, which is then spewed out into the atmosphere via the smokestacks that you see on the top of the factory. Well, one of the main pollutants that enters the atmosphere is sulfur dioxide, SO2. So that's the first one, sulfur dioxide. The other major pollutant that contributes to acid rain is nitrogen oxides. Now notice how they use an X, NOx. The reason is because there's actually multiple different, the X is a variable here. There's actually multiple different versions of nitrogen oxide. So there's nitrogen monoxide, NO, where it's just one N and one O. There's also nitrogen dioxide, NO2, and even rarely nitrogen trioxide, NO3. So there's different ways that nitrogen can combine with oxygen, but they're all pollutants. They all cause damage via the formation of acid rain. Not only are nitrogen oxides produced from factories, but also from vehicles as well. You can see that down here at the bottom of the picture. Vehicles, automobiles, cars and trucks, planes, trains, boats, anything with some sort of a combustion engine produces nitrogen oxides as a byproduct. And the exhaust that comes out of those vehicles is going to also spew nitrogen oxides into the atmosphere. So what happens then is these pollutants, they rise up into the clouds. Sometimes they fall back to the earth and then mix with water there. We call that dry deposition. But sometimes they mix with moisture in the clouds, and then when the clouds produce rain, snow, sleet, precipitation, then that's wet deposition, and we call that acid rain. So what is the chemistry of acid rain? Well, we're going to look at some complicated formulas here, but this is nothing you haven't seen before. I would like you to be familiar with these two series of reactions. and actually write them on your worksheet carefully so that you can memorize them and understand how they work. How do we get sulfur dioxide? Well, we start with sulfur. Sulfur is found in many industrial processes, and when sulfur burns, because of those industrial processes, it forms sulfur dioxide. And the reaction is actually very simple. One sulfur atom mixes with one molecule of oxygen, O2, remember Hofbrinkel, and that forms SO2, sulfur dioxide, which is a gas. That sulfur dioxide then, sorry, I should get rid of that, erase all ink on the slide. Get rid of that, okay. So that sulfur dioxide, then if we kind of continue this reaction into a second reaction, that sulfur dioxide that I started with is going to combine with more oxygen. That's going to produce sulfur trioxide. And then what happens to that? Well, that sulfur trioxide is what gets spewed, or then what mixes with water in the clouds. It could be liquid water, could be gaseous water, could be solid water, right? Could even be chunks of ice in the clouds. Regardless of what form the water is in, when that sulfur trioxide mixes with the water, we get sulfuric acid. Sulfuric acid. Okay? So understand that these three reactions are a very important contributor to acid precipitation. The second series of reactions is nitrogen oxides. Again, we use an X because it can be various types, but here's one example. So there's lots of nitrogen in the air. In fact, most of the air, about 60 to 70% of the air that we breathe in, is nitrogen gas. So that nitrogen, when it's in your car engine, there's a lot of fuel being burned, right? The gasoline or the diesel is being burned, but also some of the nitrogen in the air gets burned as well. So when you burn nitrogen, you have this reaction. NO2, nitrogen plus oxygen forms nitrogen monoxide. Then the nitrogen monoxide, so if we move down to the second row, that nitrogen monoxide burns again and produces nitrogen dioxide. And then that nitrogen dioxide gets spewed into the air and mixes with water, again in various states, and you get nitric acid. Nitric acid. Nitric. Acid. HNO3. And again, there's a little bit of nitrogen monoxide there, and that's just going to continue the cycle over again. So that nitrogen monoxide will loop back around and just keep going. And it'll keep producing more and more nitric acid. So these are two series of reactions that I would like you to know and memorize in preparation for the test. And it's also going to be an important contributor to your understanding of a project, an assignment that you're going to do next week. So what are the sources of these pollutants? Well, sulfur dioxide is a clear, colorless, toxic gas that comes mostly from industry, especially from utilities that require the burning of coal, mining and refining of metals, and the burning of fossil fuels. Nitrogen oxides, especially nitrogen monoxide and nitrogen dioxide, are mainly coming from vehicles that burn fossil fuels. I'm just looking at some interesting graphs here. Sorry, I got to get myself out of the way. Nitrogen oxide emissions, notice more than half, 56% of them, come from transportation, from emissions from vehicles. Whereas sulfur dioxide emissions, 85%, come from the combustion of fossil fuels in industrial setting. Now, what can be done about this? Don't lose hope. Sometimes this can seem kind of depressing to talk about how as humans, we're polluting the environment. But there is good news here. We actually are doing a lot of good over the last several decades. This was a real big problem in the 1960s and 70s. But since then, we've actually been working really hard to try and lower these pollutants, to try and limit limit the production of acid rain. So this graph is an example of this. So here we see electricity. The blue is electricity and heat production. Notice the blue is continuing to rise. So over the last, from 1990 to 2006, it's a little bit of an old graph now, but we're continuing to produce more electricity and more heat because there's just simply more people on the Earth to do all these things. But at the same time, we've been keeping carbon dioxide fairly flat, which is good, and we have been decreasing the sulfur dioxide and decreasing the nitrogen oxide emissions. So that's good news. Even though we're producing more electricity, more heat, we are lowering the pollution, and that's really good news. Especially in North America, we've worked really hard at this. Here's another graph which shows similar things. Get rid of my ink here. So this is actually a graph that shows from the year 1965 through to the year 2000 and almost 2010. They basically had a test study. This is a certain lake in a forest that has been affected a lot by acid rain, but they've been studying the pH of the lake over time and noticed the trend over from 1965 to 2010. So over a 40 to 45 year period, the pH is steadily getting more neutral. So the y-axis here is the amount of hydrogen ions in the water. So the acidity is decreasing, and that's really good news. So we're working hard to combat this problem. So what's the environmental impact? Well, the environmental impact is great from acid rain, which is why it's important that we work hard to lessen its damage. Acid rain changes the pH of soils, which can wash away essential minerals and destroy the ability to grow of some species of plants, especially certain crops. And this is something that helps us, right? We need to be able to grow crops. So just as an example, here are some standard crops grown around the world, some important crops, and the standard pH that they grow best in, the pH of the soil that is best for their growth. You can see some crops like potatoes, pasture lands, oats, and ryegrass are very hardy crops. They can handle an optimal pH all the way down to 5.5. So that's a weak acid, and they can still grow optimally in those acidic conditions. Now, if it goes below 5.5, they're going to be affected. But other crops are less hardy. So oil from seeds, linseed oil, wheat, corn, peas, and beans can only optimally grow at a pH of 6 or higher. And some crops are very sensitive, like these four down here: barley, field vegetables, field brassica. Brassica would be like canola crops. So things like it's escaping me now what the various types of crops that you get. But brassica basically are seed plants that you get oils from for canola oil. Also related crops would be like mustard, broccoli, cauliflower. Those would be the types of things. Cabbage, some types of cabbage. And even sugar beets, a huge source of most of our sugar. Notice these are very sensitive crops. They can't handle a pH of their soil below 6.5. So a lot of acid rain in an area is going to wipe these crops out. It's really important. So often farmers will add lime, which is a base, a basic substance. Lime can then try and neutralize the acid in the soil so that these crops can grow. It can affect forests as well. So here's a forest in a mountainous region in the eastern United States, the Appalachians, where you can see trees dying because of acid rain. And here's just an example of what happens to some of these coniferous forests. This is a normal example versus an acid rain example where the pine needles are actually discoloring because of the acidity in the soil. Acid rain also affects aquatic ecosystems. It changes the pH of lakes and rivers, and this can kill species of aquatic organisms, aquatic ecosystems. So here we see a lake that has been impacted by acid rain, and look at all the dead fish washing onto shore because of the increased acidity over time of this particular lake. Terrible, devastating impact on the ecosystem. Here we see a chart which shows you how different aquatic species can tolerate or not tolerate certain pHs. So you have some very hardy species like frogs. Frogs can handle a pH all the way down to 4 before they start dying off. But others like snails and clams and certain species of fish like bass can only handle a pH of 6 or 5.5 before they start being negatively impacted. So you get into the 2s and 3s. All of these organisms are going to perish. Here's a graph of the United States. I wasn't able to find a good one in Canada, but a graph of the United States where you see the regions most impacted by acid rain. By the way, this is southern Ontario right here. And notice we live in the region where acid rain is the worst in the United States and probably in Canada as well because of all the industrialization of this region here. So notice the standard average pH of deposition is between 4.3 to 4.5 in the eastern United States and southern part of Ontario. So we are definitely impacted by this. One last thing before we finish this off, buffering. What is buffering? Well, buffering is what we do when we try to resist changes in pH. So a buffer is a substance that has the ability to resist changes in pH. Buffers tend to be weak acids and bases themselves and often a mixture of the two. So a good example of a buffer is the hydrogen carbonate ion, which is found in baking soda. Baking soda is an excellent buffer because the bicarbonate ion can react with both acids and bases. When you add an acid to a bicarbonate ion, you get a stronger acid, carbonic acid. Excuse me. But when you add a base, like a substance with OH minus to hydrogen carbonate, you get the carbonate ion and water. And so bicarbonate is able to buffer, that is, it's able to react with both acids and bases and lower the pH or raise the pH, bring the pH closer to neutral. This is the buffer, by the way, that's found in our blood. In human blood, the pH of human blood is 7.35. It's close to neutral, but a little bit basic. And the blood has to be exactly 7.35 because the enzymes, the molecules in our blood that are doing a lot of work for our body, work best at that pH. But when we eat acidic foods or basic foods, and that gets absorbed into our bloodstream, we need a way to keep our pH staying at 7.35 and not changing based on what we eat. And so God has designed our bloodstream to have bicarbonate built into it. And so bicarbonate buffers the presence of acids and bases in this way and keeps the pH very steady. And that's what a buffer does. It keeps pH steady. That's the end of this lesson. Don't forget this is a 2-day lesson if you're feeling a little bit overwhelmed by the length of this. One last thing I'd like you to do before closing this off is go to this link here, this YouTube link. Again, I will place it in the lesson plan, and watch this video entitled pH in Everyday Life. It acts as a really good summary of everything that we've talked about in this lesson 8. And then work on some of these practice problems and make sure you reach out to me if you need assistance. And I hope that's helpful.